Alright, so in this video I'm going to talk about a certain problem that I pointed out with Coulombs law, which is the following: that suppose you have one charge over here, Q1, and another charge all very far away, Q2, and they're separated by an incredibly large distance of, say, 1 light year, which means light would take 1 year to go from Q1 to Q2. Okay, now according to Coulombs law, these two charges are exerting forces on one another. Let's just assume that they're both positive charges. So that means they're repelling each other. The force of repulsion would be extremely weak, and we will not be able to measure it. There's no question of that. It would be too weak for us to measure with our instruments, but we are not going to bother with that. So let's say that we can measure these extremely weak forces that they're applying on each other. Now here's the question, and here's actually the problem. Suppose I move Q2 just a little bit from here to here. This is an extremely tiny, maybe I moved it by 1 meter or something. Now, since the distance between the charges changed, the force between them has also changed. So according to Coulombs law, Q1 should feel a stronger repulsion, and Q2 should also feel a stronger repulsion, because the force between them according to Coulombs law is always given by F is equal to K Q1 Q2 divided by R squared. So the moment you change the R, the forces between them will immediately change, and so Q1 will know right away that Q2 has moved, and Q2 would also feel a stronger repulsion. Now, as I pointed out in class, this is a bit problematic because we know from experiments and also from the special theory of relativity that information cannot travel faster than the speed of light. So the fact that I moved Q2 and Q1 finds out immediately is not possible according to our understanding of the way nature works, and also confirmed by experiments. So that seems to be a flaw in Coulombs law, and I mentioned in class that the concept of electric fields actually solves that problem. So in this video I'm just going to briefly talk about how the concept of electric fields resolves this issue. So let me just draw this again. Here is Q1 and here is Q2, separated by 1 light year. All right, now when Q2 is moved across a little bit, so suppose I move Q2 over here. Actually, before I do that, let's just briefly talk about why, as per the field picture, how are they exerting forces on each other? So what exactly is happening? So Q2 is feeling a force due to Q1 because of the electric field of Q1. So Q1 is producing an electric field in all of space. So at the location of Q2, Q1 has a certain electric field at this location. So let's call this E1. That's the electric field produced by Q1. Q2 feels this electric field and responds to it by feeling a force. I mean, in other words, the field exerts a force on Q2. So the field is what does the pushing. So that's why Q2 is feeling a force, because it's responding to the electric field produced by Q1. Now, we know that Q1 is also feeling a force due to Q2. How's that happening? That's happening because Q2 is producing its own electric field at the location of Q1. So let's call this E2. E2 is the electric field produced by Q2 at the location of Q1. And maybe I can do this. I'll make this blue, purple, and I'll make this one blue, so you can recognize that Q1 is producing the electric field E1 and Q2 is producing the electric field E2. So Q1 is feeling the electric field produced by Q2, which is E2, and responding to that electric field. In other words, E2 is what's actually physically pushing Q1. All right, if you think of the forces like this in terms of the fields, then the problem is resolved. So what's actually going to happen if Q2 is moved slightly from where it is, if Q2 is slightly moved from here to here, this is a very small distance compared to the separation between them. This distance says 1 meter or something. Now, Q1 is really not going to find out until 1 year has passed, because that information is going to take 1 year to reach the location of Q1. So what's going to happen is that the electric field produced by Q2 is going to change, and the change is going to propagate throughout the electric field produced by Q2 or throughout space, and eventually that change is going to reach Q1, and that will happen at the speed of light. So this whole process is going to take 1 year, because light would take 1 year to move from the location of Q2 to Q1. So that change in the electric field of Q2 is going to take 1 full year to propagate to the location of Q1. So essentially Q2 was over here, so I'll just draw this. Q2 was over here, and it's producing this electric field. I'll just draw a few arrows. Maybe Q2's arrows are all purple. So Q2 was producing this electric field initially. Then when Q2 moved over here, when Q2 moved to this new location, the electric field changed, right? The pattern of electric field changed, which means that these locations now have a stronger electric field because Q2 has moved closer to them, and the locations behind have a weaker electric field. So you can see that as Q2 moves, the locations of the values of the electric field at each point in space start changing. But that change will not happen instantaneously. That change will take 1 full year to fully establish itself, I mean at the distance of Q1. So so this electric field E2 is not going to change until 1 full year has passed. And once 1 year has passed, then E2 will adjust to the new value based on the new location of Q2, and that is when Q1 will feel the force, the new force, and it will be repelled a little bit more. So Q1 is not going to find out until 1 year has passed. But the situation is actually quite different with Q2. Q2 is going to find out immediately that it's feeling a force of repulsion, a stronger force of repulsion. Why is that? Because the electric field of Q1, which is represented by the blue arrows, that electric field has already been established. So that electric field already exists at every point in space. So I'll draw a few arrows. So that electric field is there everywhere. So these blue arrows are the electric field of Q1. Okay. So there is already an electric field of Q1 at this new location. A little bit stronger because it's closer to Q1. So when Q2 moves from its initial location, which is A, to its new location, which is B, there was already an existing electric field produced by Q1 at the location B. So Q2 will immediately feel a stronger force because it's moving from a region of slightly weaker electric field to slightly stronger electric field. So Q2 will immediately feel the force of repulsion, but Q1 will not feel the increased force of repulsion for 1 whole year. So that is the resolution. That's what's actually going to happen. And it's a bit strange because it seems that we are violating Newton's third law. Newton's third law says that every action has an equal and opposite reaction. It seems for that period of 1 year, that will not be true because Q1 is exerting a stronger force on Q2. I mean, Q2 is feeling a stronger force due to Q1, but Q1 is not feeling the same force. So for 1 year, Newton's third law is not going to be valid, which is very strange. Now, Newton's third law is actually a consequence of the conservation of momentum, and Newton's third law is usually valid. There are some situations where Newton's third law is not valid, and that's not a problem. But the bigger problem is conservation of momentum. How can conservation of momentum not be valid? So let's think about that for 1 second. So suppose you have a charge Q2 over here and another charge Q1 over here, which are fairly close by. And suppose you give Q2 a velocity. initially Q2 didn't have, Q1 or Q2 did not have any velocities. If you give Q2 a velocity, now you're treating this as a system. So if you give Q2 a velocity, then to conserve momentum, Q1 must also acquire a velocity in the opposite. Actually, Q1 must also acquire a velocity because momentum has to be conserved, right, of this system. The bigger problem, though, is that conservation of momentum seems to not be working here because suppose I have the two charges Q1 and Q2 and I give Q2 a velocity, or I apply a force on Q2 and give it some momentum. Now Q2 has some momentum, right? Initial momentum. And if you treat Q1 and Q2 as a system, suppose Q2 stops eventually, but Q1 in that case has to start moving because the momentum of the system has to be conserved. You might remember experiments that we saw in Physics 1 where you had two pendulums and this pendulum came in and struck the other one, which was, and then what would usually happen is if they have the same mass, then pendulum 1 would come to a stop, but pendulum 2 would start moving. And that was the Newton's cradle experiment. So here what seems to be happening is that Q2 is being given a velocity and then it stops, and then Q1 is not doing anything at all until a whole year when it finds out that the force on it has increased, and then it will start moving. So for one full year it seems like conservation of momentum is violated. That is very strange. So what is the resolution to that? The resolution to that is the following. This part is a bit beyond the scope of this course, but I'll just mention it anyway. So in our experiment over here where the two charges were separated by 1 light year, I'll just draw them again, Q2 and Q1. So suppose I give Q2 a velocity, right? And so that means I'm giving this system, the system consists of Q1 and Q2, I'm giving it some momentum, right? And Q2 stops over here. Now what happened to the momentum of Q2? We're ignoring friction or anything like that. So if Q2 stops, what happens to the momentum of Q2? The answer is the momentum goes into the field. So one really fascinating thing about electric fields is that they can actually carry energy and momentum. We will not discuss that very much in this course, but fields can also carry energy and momentum. So when Q2 stopped, its momentum actually went into the field, and that momentum is actually traveling with the field from Q2 to Q1. And then that momentum also cannot travel any faster than the changes in the field can propagate. So it's going to take one full year, and then that momentum will get to Q1, and then Q1 starts moving. So when Q2 stopped, it's not like its momentum disappeared. It cannot, because momentum is actually conserved. What ended up happening was that the momentum was actually carried along with the field, which is really hard to imagine how momentum can be carried by the field, but it can. And the momentum was traveling along with the field, with the changes in the field, and then eventually took its time, one year, and eventually reached Q1, and then Q1 acquired that momentum and started moving. So conservation of momentum is valid if you realize that fields can actually carry momentum.